How does something travel through nothing?
What are you talking about, Albert?
I imagined I was riding alongside a light beam.
Yeah, of course you love these cool scenes, like when the Flash in the Justice League movie moves so fast it's portrayed as if time stops. Quicksilver in X-Men shows the same thing. While this is just fiction, did you know that this scene is similar to what Einstein imagined when he formulated the theory of relativity? His biography mentions that when Einstein was 16 years old, he wondered what it would be like if he were moving at the speed of light.
Einstein, wake up!
I wasn't sleeping, sir. I was thinking. When you were traveling the speed of light alongside the wave, me, I appear frozen in time.
10 years after this youthful imagination, Einstein successfully formulated the theory of relativity, a theory that radically challenged the laws of physics by stating that time is not absolute.
What do you say? Time is not absolute.
Time can be faster, slower, or can even stop, depending on how fast you're moving.
The faster we move through space, the slower we move through time.
What's the logic behind this, and how did Einstein manage to change people's perception of time? Watch this whole video. We're going to break down Einstein's crazy mind. According to you, how can something be considered moving? Well, obviously, when it moves from one place to another. But in physics, it's not that simple. Look at this falling ball. Nothing seems wrong at first glance, but actually, the ball is falling onto a moving board. You don't notice the board is moving for two reasons. First, the ball falls normally, exactly as if the board wasn't moving at all. Second, you're viewing it from a camera perspective that is moving with the board. In physics, this is called an inertial frame of reference. The bottom line is, you won't feel any change in physics as long as the frame of reference is stationary or moving at a constant velocity.
If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity.
This is precisely what we experience on Earth. We feel like the Earth is still, even though it's constantly spinning at a speed of about 1,600 kilometers per hour. We don't feel it because the speed is constant. It's the same when we're on a plane. Once the pilot announces that it's safe to remove your seatbelt, you can do normal activities. You can eat and drink as usual, and you can even walk around as if the plane isn't moving, despite the plane's speed potentially reaching 800 kilometers per hour. Now, this situation causes one problem.
Here, the cart moves by, the ball will fall, and you can watch in the slow motion camera.
As soon as you change your perspective and step outside that frame of reference, you can no longer measure motion the same way as before. In the case of the ball, when the camera is moved to the table, its trajectory isn't straight. It becomes a parabola. This is called relative motion. Relative motion is what bothered Einstein. Why? Because ultimately, there is no single reference point we can use as a benchmark to measure motion absolutely, because everything is moving. So, Einstein reasoned if all speeds are relative to their own frames of reference and there's no absolute reference point, then what does time relate to?
Now I'm imagining that the ball is traveling in deep space. There's no stars or planets around it. Acceleration is the derivative of velocity with respect to time. But how do you know that the ball is moving at all if there's nothing to compare its motions to? In other words, what is time?
When we describe motion, we do so as a function of time. 10 meters per second, 100 miles per hour. Is time universal? In other words, is there an audible tick-tock throughout the galaxy?
The answer to Einstein's question was found in light. Light is what made Einstein think that time too is relative.
But you and I both know that time can't move at different speeds. Unless it could.
Many of you might think that light is instantaneous. You'd flip a switch and the area's lighted up. But light actually takes time to travel, which means light has a speed. However, there's something strange about the speed of light, and it confused all physicists in Einstein's era. It was already common knowledge that light is a wave, which was proven by Thomas Young with the interference of light. But light being a wave posed a problem. Waves are fundamentally disturbances that propagate through a medium, like, for example, water. When you drop a stone into a pond, a disturbance is created, and that disturbance propagates across the water. Same goes for sound. Sound is a disturbance that propagates through the air. So if water waves propagate through water and sound propagates through the air,
In this case, the medium is a disturbance of the air, which, when it hits your eardrums, is interpreted as sound.
then what does light propagate through? This was a mystery at the time, especially since light can pass through a vacuum. For proof, if you put an alarm clock in a vacuum chamber, you won't hear it sound because there's no air inside to transmit the sound. But light passes through the vacuum. You can still see the alarm clock vibrating.
The fact that they could see inside it meant that there still had to be something left in there. Just as air carries sound waves, they believed there had to be a medium carrying the light waves.
Therefore, at that time, scientists suspected there was an invisible medium which they named the luminiferous ether or aether.
Scientists think that light travels through its own special invisible medium. They call it the ether.
Unfortunately, all experiments conducted by scientists to detect the presence of the aether failed. The most famous experiment was performed by Michelson-Morley. They tried to detect the aether using a device often called an interferometer. Feel free to look up how this device works, but what's certain is that through this device, they couldn't prove that the aether existed. This problem perplexed physicists. How can light travel through something that doesn't exist? And the consequence was even more confusing because light doesn't need a medium, so light doesn't depend on any frame of reference, so its speed is always constant, 300,000 kilometers per second, as measured by Michelson-Morley.
But it's a safe bet that, given the scientific consensus at the time, they were convinced that the ether really existed. So they'd have been sure that they would have found light traveling at different speeds as it moved in different directions. But it didn't. No matter how they rotated their apparatus, they always found light traveled at the same speed.
This phenomenon had been bothering Einstein since high school, since he was 16.
How does something travel through nothing?
What are you talking about, Albert?
I imagined I was riding alongside a light beam. Guess what happened?
At that time, Einstein imagined himself riding his bike to keep up with the beam of light.
Imagine I'm a light beam traveling to Earth. Now catch me!
How fast must we go?
About 300,000 kilometers a second!
And when he caught up, he imagined the light stopping.
When you were traveling the speed of light alongside the wave, I appear frozen in time.
Einstein didn't fully understand what it meant at the time, but 10 years after this youthful imagination, Einstein successfully formulated the theory of relativity. Einstein began to think that time...
I've completely solved the problem.
What are you talking about?
Close your eyes. Pretend you're overlooking a train track.
is not absolute because what is absolute is the speed of light. Einstein asked us to imagine a situation like this. Picture yourself standing by a train track and watching a super fast train go by. Then you see two lightning bolts strike simultaneously on both ends of the train car. For you, standing by the track, the two lightning bolts happen simultaneously, but not for the person in the car. Remember, for you to see something, light must reach your eyes, and the speed of light is always constant. So in this situation, you on the track and the person in the car will experience different times. From this, Einstein formulated his theory of relativity using light as the absolute reference. Aided by the mathematical formulation called the Lorentz transformation, Einstein showed us that time will be different for everyone.
To me, standing still, they were simultaneous. How could the two of us experience the same event differently?
We couldn't. Unless
Time is not absolute.
The faster we move, the slower the time we experience. This phenomenon is called time dilation. According to Einstein's relativity, the reason we all feel time is the same is because our normal speeds are very far from the speed of light. If you plug our speeds into the formula, the time difference factor is almost non-existent. But if we could move close to the speed of light, say 80% the speed of light, time can slow down by a factor of 2. At 99% of the speed of light, time can slow down by a factor of 7. At 99.99% of the speed of light, time can slow down by a factor of 70. Yes, that's relativity, guys. It sounds crazy and fictional, but physicists say that no matter how strange it is, that's how the universe works. In other words, light is the reason why we see the world as it is. But there might be one more question on your mind. What if we move at 100% of the speed of light? Then time no longer applies. That means that for light, time does not exist.
But if we'd have sent Jim off in a rocket, that we catapulted Jim off at 99.94% the speed of light. So for him, the journey would take 10 years. But for us, with our watches ticking faster than Jim's, 29 years would have passed.
When I'm up there in hypersleep, or traveling near the speed of light, or near a black hole, time's gonna change for me. And it's gonna run more slowly.